Welcome to the solutions to the Thermodynamics Problem Set, problems number 7 through 12. Number 7, on a very hot day, it's possible to cook an egg on the hood of a car. Would you select a black car or a white car on which to cook your egg? Explain your choice. The concept that you're being questioned on here, number 7, is the concept of radiation. And what you would do is you would choose a black car because it's a better absorber and radiator of thermal energy and is known as a black body. You may have heard the term black body radiation before, but this is why you would select the black car as opposed to a white car. Number 8, in a daring demonstration, a professor dips her wetted fingers into molten lead at 327 degrees C and withdraws them quickly without getting burned. How is this possible? Well, let's go over to our buddies at Mythbusters and have them answer that question for you.
You look like you're thinking of something pretty good.
I am. There's a myth going around that you can stick your hand into molten lead and not get hurt.
Molten metal. It's pretty nasty stuff. Just look at these shots of a foundry. It would seem that if you touched any of that stuff with your hands, you'd be horribly, horribly burned. But maybe not so. See, there's a myth going around that if you take pure lead and you melt it, that you can dip your hand in it and not be burnt or horribly injured. I know. The trick is supposed to be that you wet your hand before doing it, and it exploits what's known as the Leidenfrost effect.
The Leidenfrost effect? Well, seeing as it's the scientific basis for the myth, Adam, with his hot steel ball and fish tank, is on demonstration duty.
Wow! Look at that!
You can see a clear skin of, I guess it's steam around the whole thing. What you're seeing in this demonstration is known as the Leidenfrost effect.
It's like an atmosphere.
It's interesting because the steam that's created when you expose a hot surface to water is actually insulating that surface. And it makes sense because steam, being a gas, conducts heat less rapidly than the water itself does.
And that's the key. When cool water is exposed to an extremely hot surface, a layer of water vapor, which is a relatively poor heat conductor, provides a thin protective barrier. So it's time to get cooking for this hair-raising stunt.
Is this me?
With the one and only ingredient, lead.
Is this the first Terminator you've ever cooked?
No, I've done this a lot before, actually. Every time I get a robot that's misbehaving.
The problem is you gotta keep them cooking, otherwise they reformulate and try and kill you. It's about 725 degrees.
Well, that's about 100 degrees more than melting temperature. I think that's about right.
Let's do it.
Cue the stand-in digits.
This meat is raw, and if it actually gets too hot, it's going to change color because it's cooking.
If these finger-sized sausages sizzle, then Adam and Jamie won't be going anywhere near the hot pot.
Oh no, that seems to be a problem, doesn't it?
A very slight change of color.
But also, lead stuck. I wouldn't want that to happen to my finger.
No.
While not burnt by the standards of any backyard barbecue, the sausage is being cooked. But they're not giving up yet.
A hair's breadth over 800.
In order to avoid burning their stand-in digits, they're going to raise the temperature and try again.
Here's where we stand so far. Behind me is a bucket of molten lead, into which we've already stuck a couple of breakfast sausages and watched them get lead stuck to them and watched them get burnt. We're not ready to put our hands in there yet, but we hear that if we get the lead 200 degrees over its melting point, great.
That's 850. Let's try it.
It'll stop sticking.
Here's that finger, bucket of water. Whoop. Shake it off. Into the lead. And it looks pretty much perfect, and it's still cold.
Yeah.
So 850 degrees Fahrenheit is the magic number. The sausage comes through unscathed, which leaves just one question.
I'm game. You game?
I picture people yelling at their TV, "Go on, do it! You, go on, try it!" Ah! Aren't you? Yeah. All right. We're about to go for it. We're about to dip our hands into molten metal, and we've got plenty of evidence saying that this is safe. It's clear from our experimentation that the conditions to do it safely are actually pretty precise. I think we've got them. And I think it's going to be okay.
And this little piggy burned clean off.
Despite the sausage-based evidence, clearly a sentence never before used, there is still a healthy amount of trepidation. Remember, the lead is at around 450 degrees Celsius, which puts this stunt firmly in the don't try at home category.
Nothing. Now, I just went about that deep.
Yeah, you want to go a little deeper?
My little finger is just fine. Of course, I only went in about that deep. I was being a little careful. I didn't feel a thing. It felt kind of warm and pleasant, actually.
Go for it.
And a repeat performance with an index finger yields the same result.
Now, that went in pretty good, and no problem.
No problem?
No problem.
I guess it's my turn.
Adam has had the luxury of using Jamie as a human guinea pig, so naturally he has to up the ante. He's going for 4 fingers.
Here we go. Ladies and gentlemen, one human hand in molten metal. Oh, that's freaky. You can feel the water boiling against your fingers. You can feel that right there.
And that pretty much puts this lead mini-myth to bed.
So Jamie and I just successfully dipped our hands into a pot of molten metal. No lie. The lead and frost effect is no myth. It protected us. Well, I'm unharmed. You?
I'm fine.
That's all we needed. That's a myth confirmed.
Yep.
And there you have it. Pretty neat episode there. Number 9, ethyl alcohol has about 1/2 the specific heat of water. Compare the temperature increases of equal masses of ethyl alcohol and water in separate beakers that are both supplied with the same heat. Well, if we take a look at the heat equation, Q equals mc delta T, ethyl alcohol has half the specific heat. So if it's supplied with the same amount of heat and it has the same mass, it would result in a change in temperature that's twice as great as for the ethyl alcohol as compared to water. Number 10, how many joules of energy are required to raise the temperature of 100 grams of silver from 20 degrees Celsius to 100 degrees Celsius? Well, we start off with a Q equals mc delta T equation. We substitute. We have to have our mass in kilograms. We use our textbook or Google the specific heat of silver, which is 235 joules per kilogram degrees Celsius. That's why your mass has to be in kilograms. It's also why you're allowed to leave your temperature units in degrees Celsius, because the specific heat has those units in it. So we put our change in temperature, 100 minus 20 degrees, and we get us the heat required to raise it to 1,880 joules. Pretty straightforward, easy calculation. Number 11, a 200-gram aluminum cup contains 800 grams of water in thermal equilibrium with a cup at 80 degrees Celsius. The combination of the cup and the water is cooled uniformly so the temperature is decreased 1.5 degrees Celsius per minute. At what rate is the energy being removed? Express your answer in watts. That last sentence is a dead giveaway here, asking you to express your answer in watts. Whenever you hear the rate at which energy is added or removed from a system, what you need to hear is power. So what we need to do is calculate the energy that's required to decrease the temperature 1.5 degrees C from the given quantities. And since that's done per minute, if we divide that energy by the time, that will give us the rate at which the energy is being removed. So you can see we have a Q equals mc delta T set up here, but we have an mc delta T for the water, and we have an mc delta T for the aluminum cup. We go ahead and substitute. We've got 800 grams of water, 0.8 kilograms. Specific heat of water, 4186, and our change in temperature is 1.5. Our mass of our aluminum is 0.2 kilograms. We look up the specific heat of aluminum and find it to be 900, and our change in temperature is 1.5. That gives us a total heat lost of 5,293 joules. We now take that 5,293 joules, divide by 60 seconds, and this would give us 88 joules per second, which of course would be the same as 88 watts. That's how you would do that. Lastly, number 12. 100 gram aluminum calorimeter contains 250 grams of water. The two substances are in thermal equilibrium at 10 degrees Celsius. Two metal blocks are placed in the water. One is a 50-gram piece of copper at 80 degrees Celsius. The other sample has a mass of 70 grams and is originally at a temperature of 100 degrees Celsius. The entire system stabilizes at a final temperature of 20 degrees Celsius. Find the specific heat of the unknown second sample. This is a calorimetry calculation, so we start off with heat gained equals heat lost. We're going to put all the substances that gain heat on the left side of the equation and all the substances that lose heat on the right side of the equation. Well, the substances that gain heat are both the water and the aluminum calorimeter, the aluminum cup, and the substances that lose heat are the piece of copper and the unknown. So we have the mass times the specific heat. The temperature changes from 20 degrees Celsius, from 10 degrees Celsius to 20 degrees Celsius for the aluminum, as well as the water, which is 0.250 times its specific heat, 4186, times its change in temperature. Here we have our 50-gram piece of copper at a specific heat of 387, and it undergoes a change in temperature of 60, from 80 degrees down to 20. We have a 70-gram, 0.070 kilogram piece of unknown sample, unknown specific heat, which is what we're looking for, and it too undergoes a 80 degrees Celsius temperature change. Do the algebra and solve for C, and you get a 1,820 joules per kilogram degrees Celsius specific heat for the unknown second sample. More to come with 2 more problems in class tomorrow.